What are boundary conditions for mechanical engineering vibration modes? Have you ever wondered how engineers predict how structures will vibrate? One key factor in this process is boundary conditions. These conditions define how a structure is supported or constrained at its edges. They play a major role in determining how a structure can move or deform during vibration. Let's break this down further. Boundary conditions come in several types. First, we have the clamped or fixed condition. Here, the edge is held rigidly, which means there is no movement or rotation allowed. This condition increases the stiffness of the structure, leading to higher natural frequencies and lower vibration amplitudes. Next, we have the simply supported condition. In this case, the edge can rotate freely but cannot move up or down or side to side. This allows for some movement, resulting in lower natural frequencies compared to the clamped condition. Then there is the free condition. With this setup, the edge is completely unconstrained. This means both movement and rotation are allowed, resulting in the lowest natural frequencies and the largest vibration amplitudes. Another option is elastic supports. These are modeled as springs that provide partial restraint. This setup allows for behavior that falls between fully fixed and completely free. Now, how do these boundary conditions impact vibration modes? They affect the mode shapes by either restricting or allowing certain movements at the boundaries. For instance, a clamped edge forces zero movement and zero slope, shaping the vibration pattern accordingly. Natural frequencies are also heavily influenced by these conditions. A clamped beam vibrates at higher frequencies than the same beam with simply supported or free edges. In more complex structures, such as beams or plates, boundary conditions can influence both torsional and bending vibration modes differently. In practical applications, understanding boundary conditions is essential. In aerospace and automotive engineering, for example, knowing how to design components can help avoid resonant vibrations that might lead to fatigue or noise. In civil engineering, these conditions are critical for predicting how beams and plates in buildings or bridges will respond to dynamic loads like wind or earthquakes. For springs and rods, the way they are mounted or connected can significantly change their vibration characteristics, which is vital to consider in mechanical system design. Real-world boundary conditions often do not fit neatly into these categories. They can be modeled using spring constants for both vertical and rotational constraints. Different beam theories show varying sensitivity to boundary conditions, especially at higher vibration modes. Additionally, factors like rotational inertia and torsional stress in elastic rods or rings interact with boundary conditions to influence vibration modes. Understanding boundary conditions is essential for accurately predicting how mechanical structures will vibrate. This knowledge ensures safety, reliability, and performance in various engineering applications.